let me just review what we have been doing so far, just so that I'm sure that whatever I've been talking about has been clear to everybody. So we said that look, an operating system is supposed to sit at the lowermost layer of the hardware, just above the hardware, and it's supposed to provide an interface to the applications so that they can access the hardware or other shared resources. Some examples of shared resources are devices, CPU itself, memory, files, right? So all these are examples of shared resources, and the operating system sits on top of all these shared resources, and only the operating system has direct access to these resources. Things like printer, monitor, keyboard, file system, all these only the operating system has direct access to. An application is supposed to make requests to the operating system to be able to satisfy its functionality. All right. We also said that an operating system should be capable of running multiple applications at the same time. And so we looked at UNIX, and UNIX has this notion of process, right? So a process is a container in which a program can run. The container has completely private memory, so it is completely isolated from all the other processes in the system, right? So it can it can allocate memory for its variables, do some computation, and nobody else will be affected by its computation, and nobody else can disturb its computation. So we understood that much, but we said that a process within a container by itself is not very useful, because you are in this sort of closed boundary, and if you cannot interact with the outside world, what's the use? So to be able to interact with the outside world, an operating system provides what are called system calls. Okay, so each process will make system calls to do different things. And we said that there is a system call called fork that allows a process to create another child process, and that child process has identical contents as the parent process. Right? Then there is another system call called exec, which allows a program to say that I want to load another program. Right? It can name the program using a file, and it can call exec on that file to load that program with its arguments. And so that program will start running, and the old program will be wiped out. Okay? So we said that if a process wants to create a new process and load another program into it, one way to do it is to fork itself. So there are two copies of itself that are running, and in the child process call exec. Right? So that's last time. So you divide this this job of creating a process and running a program into two separate system calls. One is fork, and the second one is exec. Right? And we saw that why is it useful to actually divide this job into two things, because after you fork, you can change the environment of the child process before you call exec. For example, you can change the file descriptor table. Right? So we also said that every process has an associated file descriptor table. Right? A process cannot access its own file descriptor table directly. It can only manipulate the entries of its file descriptor table using open and close system calls. Right? So we saw two more system calls, open and close, and so a process is allowed to manipulate its file descriptor table using open and close system calls. Right? So now what if you wanted to spawn another process, but you wanted to spawn it in a different environment than your current environment, then you would first spawn a child process, change the environment of the child process, and then call exec. Right? So that way you can actually, between the fork and the exec, you can have more system calls like open and close to change the environment of the child process before you actually execute that process. Okay. We also said that once a process is forked, its environment is also copied. So the file descriptor table of the parent process is copied identically to the child. Right? and if the child wants, it can change its file descriptor table using open and close calls before it calls exec, for example. We also said that on Windows, for example, Microsoft Windows, you don't have this fork and exec. Instead, you have one system call that's called create process, and that will do both these functionalities. It will fork a new process and it will load the executable in that process. But notice, because you have just one single system call to do this thing, I cannot set up the environment of that process before I start it. Right? I can only change my own environment. I cannot change the environment of the other process after it has started. So the create process system call actually takes a lot of arguments to be able to specify all the environment variables of the child process. So as an operating system designer, you are basically choosing what kind of system calls do you want to expose to the process. The UNIX system call designer said that, I think fork and exec is a more elegant way of doing things. The number of arguments to each of the system call are small. The semantics are very intuitive, right? And so this is a better way. The Windows operating system designer thought other ways. He said, I don't want two separate system calls. I want one system call, and but that system call will now need to have lots of arguments, right? So it's when somebody is designing an operating system, there are these kind of trade-offs that one needs to worry about. The trade-off is between design simplicity. One can say that Unix's system call is very simple design because very clean interface, very simple system calls, as opposed to design complexity because the system call like create process has roughly 10 arguments, which is a lot of arguments and a lot of initialization to be done by the user. So it makes things a little complex. On the other hand, it can be argued that create process is more efficient because you just start a new process and load an executable right away. On the other hand, in fork, you have to start a new process, copy the contents of the parent process to the child process. And this copying may be the extra work that you're doing. But after you copy, the next thing you do is called exec, then all that copying effort is wasted because you're just overwriting the child with the new process, the new image. So one can say that maybe create process can potentially be more efficient, faster. But in practice, it turns out that fork and exec is not any less fast because you can do optimizations. You don't need to copy the entire content of the parent into the child. And these kind of optimizations we are going to look at later. Okay. So all I want to motivate is that an operating system designer can choose to design its system calls. Different designers may choose different types of system calls. But more or less, the modern operating systems today are based on Unix's model, where even though Windows doesn't have fork and exec, it has all the other ideas from Unix like file descriptor table. So each process has a file descriptor table. Each process can make open and close system calls. Each process can make open and close system calls to open and close files or resources, and it can make read and write system calls to access those resources. Right? So these are pretty much common to all the modern operating systems. Right? I will also point out here that these operating systems were largely designed for uniprocessor systems, with a single CPU in the system. Today we are having a situation where hardware has lots of CPUs, multiple cores in one machine, and so often there's a lot of debate. There's a debate that goes on in our research community that should we change our operating system abstractions? So should we redefine our system calls so that they better reflect the current hardware? Right? For many reasons, these system calls, while they work, they are not so fast to implement. They do not use the full capacity of the hardware today, right? And various ideas are being proposed to be able to improve the situation. Okay, just to throw things in perspective and give you another example of how underlying hardware can dictate what kind of system call interface should be. All right. So once we have this, so let me just write what are the system calls that we've seen so far. There was fork, there was exec, there was open, there was close, read, write, and then we also saw exit, that basically says a process wants to exit, and then there's a system call called wait. It basically says I want to wait on a process on one of my child processes to exit, right? And using these system calls, we have seen how the shell is implemented, right? The shell is nothing but a program, and the program gets loaded as a process, and this program just makes system calls to implement all the functionality that you see, right? It's a very common program. I mean, on Windows it's called the command prompt, and on Linux it's called the shell, right? And so it's a very common program, and heavily makes use of the functionality of the UNIX system calls, right? So for example, we saw that the shell can be used, so let's say this is a shell, it can be used to make a command, so some command. And when you type this command, what happens is the shell first forks, so it basically this amounts to forking plus execing of command, roughly speaking, right? Fork basically creates a child process, and in the child process you execute the command. The parent process also calls wait on the child process, right? So basically what happens is the command executes. As long as the command is executing, the parent is stopped on wait. It's just waiting for the command to finish. And as soon as the command finishes, and it indicates its its completion by calling the exit system call, the wait in the parent returns, and the next dollar sign is printed. Okay. We also saw that the shell can do redirection. So if you say command greater than some file out, what this amounts to is fork. You create a new process once again, but before you exec, you say close on one, you close the first file descriptor, and you open out. So now the standard output gets redirected to the file out, and then you call exec. Right? So this allows you to do redirection, right? So we said that this was called output redirection. Okay. If there are any questions relating to this part of the course, this part of the material, please ask now, because I'm going to start more advanced topics after. I mean, I'm going to start building upon this. So if you don't understand this, it'll be hard for you to follow what I'm going to discuss next. So if you have any questions, please ask now. All right, good question. What happens when the child process executed using fork and exec is larger than the parent process? Okay, no problem. Even if the child process that was exec is larger, the operating system is supposed to allocate more memory to the process. So initially when you forked, you had a small amount of memory that was equal to the memory that you had in the parent process. But when you called exec, the operating system knows that you need more memory, so it will allocate more memory. So it can be larger, no problem. Okay, there's a question from SMIT. SMIT? Please ask a question. Cannot hear you. Okay, so I don't. Okay, there's another question from SMIT. Let's try again. Please ask a question. Please ask a question. Cannot hear you. Cannot hear you. You can type your question because we cannot hear you. I think there's some problem in with the microphone there. Okay, let's see if there's a question on chat. Okay, so if there are no questions, let me proceed. So we have seen redirection. So there's a question, why did I use the close system call? Recall that close system call deletes an entry or removes an entry from the file descriptor table, and open looks for the first available entry. So after you close one, open is going to look for the first available entry, and it's going to find that one is the first available entry, and it's going to fill it up, right? And so that's what we wanted. We wanted to, the close is used to basically free std out first, and then open is used to refill it with something else, some other pointer. Okay, the question is, but if we already have an empty FD, so what if at 1 it was already empty, so there was nothing at 1 already. So no problem, if you call close on an empty FD, it just does nothing, right? It just returns an error saying that, I couldn't close anything. So you just close it to be on the safe side. In general, when you start a process, you are expected, so one of the conventions is that 0, 1 and 2 should be pointing to valid values, so they shouldn't be empty. So all these three should be pointing to valid values, because the program may want to write something to its standard output, read something from its standard input, and also write something to its standard error, right? So in general, as a convention, 0, 1 and 2 are filled. Okay, I'll continue. All right. We also said that, look, the previous syntax allowed redirection to a file of the standard output. I could also say command and redirect using the standard error using this syntax called 2 greater than, and I can say 2 greater than out, let's say. In which case I will do fork plus close 2 in this case plus open out plus exec command. Right? Fork itself, the parent itself will just call wait. Wait for that process to finish. After which it will print the next dollar sign. Okay. We also said that the child could when it calls, so exec is eventually going to call exit, and the argument of exit will be some code which is called the exit code, which is just a number, right? Which is a number which is an 8-bit number, let's say, and the parent can read that number through its wait system call. So that's a one way of doing inter-process communication. So the child can indicate its return value or its exit code in this way. So the child exits using by specifying certain code, and the wait system call can read that code, right? And this is typically used to indicate success or failure of the child process. So did the child process succeed? Did it fail? Did it fail for a certain reason? All these information can be communicated using this exit code mechanism to the parent, right? So we also saw an example where the shell may want to print to the user why something failed, right? So if something failed in the child process, then the child process will exit with that value of the failure code. When the parent is going to return from the wait system call, it will be able to read that value, and using that value it may want to print something to its own standard output, indicating what happened to the child process. What happened to your command? Did it execute? Did it fail? You may want to do different things with that. So this is one form of inter-process communication. In this case, we saw that the inter-process communication is happening from the child to the parent through the exit and wait system calls. Only one byte of data is communicated in this way, and it is only communicated when the child is actually terminating, and the parent is waiting on it. Okay. All right. How does the system call work from SVEC? Let's just assume that system calls are just functions that are provided by the kernel. How they are implemented, we are going to discuss later. Let's first understand what kind of system calls exist. Right? Let's first understand what is the interface. Then we'll discuss about implementation of that interface later. Okay. So for now, for our discussion, let's just assume that a system call is nothing but a function call. There's another question, how can a child process be larger than the parent process? Why not? I mean, a child process can be larger than the parent process. So let's say this is the, and this was parent. It called fork. So what happened was when it called fork, the child was identical to the parent. So this is the child. But let's say then it called exec, and the file exec is actually much bigger, and so this child will actually grow in size. And by growing in size, I mean it's all this, the space inside the rectangle, I'm representing it to say it's memory. So this is all the memory space of that child. So it's possible for a child to be bigger than the parent, no problem. Okay. All right. So we also said that internally the file descriptor table is implemented like this. So let's say UNIX FD table. Here are the descriptors 0, 1, 2, 3 and so on, and then each of them points to a structure which also has an offset inside it, right? And it has a pointer, let's say, to a file. So let's say it was pointing standard out, so it's going to point to this place, right? And when I call a write system call on, let's say, file descriptor 1, it just writes starting at this offset. Okay. So that's how it knows where to write. When you say write 1, some hello, then hello is written at that offset, whatever is stored in that structure. Right? Recall that we are not providing the offset explicitly in our write system call. The semantics of the write system call are that just write at the current offset wherever you are. Right? And also each time you write something, the offset gets incremented. Okay. We also said that if a parent, let's say this is parents FD table, and this is child's FD table. It's going 0, 1, 2, 3 and so on. And it's going 0, 1, 2, 3 and so on. Once you fork something, they are identical. Right? So as soon as you called fork, the FD table is copied completely to the child. But notice that it's only a copy. So if there was a pointer from 1 to some structure which said, you know, file name out and offset 45, then even here it's pointing to the same place. So this way they are sharing this file. If one of them calls write, it will increment the pointer 45. Let's say it said hello, which is a string of length 5. So it will increment 45 to 50. And if the other one says hello also, then that will increment 50 to 55. And so their outputs will get interleaved in that file. Right? So this is one way of sharing files between processes. Okay. Notice that in this way of sharing, the offset itself is shared, right? So if one process calls write, offset gets incremented. If another process gets write, offset further gets incremented. On the other hand, if you were not doing this kind of sharing, if on the other hand, let's say this was the parent and this was a child, and this is 1, this is let's say entry number 1, and this is pointing to out 45, right? And this is also pointing to another structure. They are internally pointing to the same file out, and let's say it's also pointing at 45, right? This is possible if the child was created, but after the child was created, the child made an open system call on out, and has been writing something, so the offset has already reached 45. Okay, but notice that this situation is different from the situation that we had earlier. Now, if the parent calls write, the data is going to be written at offset 45. So, and when the child calls write, the data is again going to get written on offset 45. So they are going to overwrite each other. So if one says hello and other says world, you will only see one of the data. You will not see them appended to each other. You will only see one of them, because the offsets are not shared now. The offsets are separate, and so each of them is incrementing independently, and so you will be basically you'll start to overwrite each other. Okay. In general, this is not a recommended situation that you open the same file in multiple places simultaneously, and the user should take care of not being able to not doing that. Okay, so that's a responsibility of the programmer. However, the operating system allows multiple processes to open the same file, in which case they may be overwriting each other's data. Recall that in the previous case, I only called open once and fork just copied the file descriptor table, so the offset itself got shared. In this case, the offset is not shared, and so you are overwriting each other. Okay, are there any questions on this part? So just to clarify, when you call the open system call, you initialize this block again, right? If you can point here, you initialize this block again, and depending on the arguments to open, this offset gets initialized to either 0 or to the end of the file. Okay, so if these two processes called open independently, they will potentially have the same offset and they will keep overwriting each other. On the other hand, if it was pointing here, then they will not overwrite each other, they will append to each other's output. They have a shared offset. So this is something that you should understand. Okay. So in the same vein, the shell allows you to have a syntax which says command greater than out. Okay, and it also allows you to say 2 greater than and 1. Okay, this is again a syntax which basically says redirect the standard error to the same place where standard output is living. Right, so whatever is standard output, just redirect standard error to the same place. That's what 2 greater than and 1 means. Okay, and so in this case, what's going to happen is you're going to say fork, then you're going to say close 1, open out, right? Then you're going to say close 2, because you also want to redirect the standard error, and now you're going to say open. Could somebody answer this? What should I say here after close 2? So, can one of the students want to answer this question? What do you want to say after close to in this case? So please just raise your hand. Will you go to users? Nobody? Once again, so is there a question? I mean, did you not understand the question? If so, please also ask. Okay, SMIT. SMIT.
So please repeat the question.
Okay, the question is, let's repeat the question. Could you focus on the page? Okay, so the question is, this command, the shell allows you to redirect the standard output using the greater than sign and specify the file name. So it basically means that redirect the standard output to this file. And then it also allows you to say that redirect the standard error to the same file. That's what 2 greater than and 1 means. So whatever standard output has been redirected to, redirect standard error to the same point, to the same place. So if standard output is redirected to monitor, then 2 greater than and 1 will redirect standard error to the same place, right? If standard output is redirected to a file, then standard error will also be redirected to the same place. So my question is, to be able to implement this, recall that if I didn't have this, all I would do is fork, close one, open out, and exec. But now because I have to redirect standard error to the same place as standard output, I need to close standard error and then what? Question is, what do I need to do here? Okay, CE Pune.
Hello? Hello?
Yes, please.
After closing this two, we can open same file in append mode.
Open
Open out in append mode.
Okay, open out in append mode. Great, thank you very much. So you say that open, so one answer that's been given from CE Pune is open out in append mode. Okay, this is one answer. Let's see what happens if you do this. Okay, so what will happen is that let's say this is the file descriptor table. And this is file descriptor number 1. So 1 will now point to out at offset 0. Let's say the file wasn't existing in the beginning. So this is 1. And now 2 will again point to a different structure because open will just initialize a different structure out. And when you open it in append mode, the offset gets initialized to 0 again, right? Because the file was empty at the time you opened it. So it gets initialized to 0 also. Now if you're going to say write, 1 hello, 5 characters, and then you say write to standard error, let's say you want to say some error condition, so you write the string error and 5, then what will happen is that they will overwrite each other. The first system call is going to write hello in from the 0 to 5 bytes, and so this will go to 5. But then when you say write to error, then this is also going to go from 0 to 5. And so error will overwrite hello. Okay, and you didn't want to do that, right? You wanted the outputs to get appended to each other, right? So this is not a great picture. So this is not a great idea. What you instead wanted was a picture which looked like this. Let's say this is my FD table, and this is file descriptor number 1, and this is file descriptor number 2. One should be pointing to out and 0, and 2 should also be pointing to the same structure. That's what you wanted, because now if you're going to call write hello, write on 1 and write of 2, the two outputs are going to get appended to each other, right? How do you do something like this? The open system call is not going to do this for you, right? So you need a different system call. So Unix has a system call called dup. Okay, and you can specify a file descriptor as an argument to dup, which basically just copies the value at file descriptor number fd and allocates a new file descriptor table entry, right? So in this case, if I did close 1, open out, close 2, and instead of open out in append mode, I did dup 1, that would have done it, right? The semantics of dup is that it will copy the contents of the file descriptor table at value 1 in this case into the first available file descriptor starting from the beginning, and the first available file descriptor starting from the beginning is 2 because you just closed 2, and so 2 is going to get an identical copy of 1, right? So close 1, open out, close 2, dup is going to implement this functionality, all right? Yeah, just okay. Any questions on this? Okay, SMIT, please chat, please type your question because I think there's some audio problem. So please type your question in the questions using the text format. All right. Okay, so so that allows this kind of thing, right? So you can use dup to point the same thing to the same place. Okay, so we have studied a lot about how redirection works, how open syst close, and we have seen a new system called dup. But let's look at these things in practice. All right, so let's take a real world example where these things can be useful. So let's say I had a program called sort, right? Actually, this is a real program on Linux called sort, and what this program does is it takes a file from standard input. Okay, so it just calls read on standard input. So calls read on file descriptor number 0 till the input is finished. Sorts, reads it into memory, its own memory, right? Whatever memory it has allocated to itself, and then sorts it, and then writes it to standard output. Right? So if you, for example, type sort on the shell and then you type some strings separated by the new line character, enter. So if, for example, if I say, sort, and then I say hello CE Pune, and then I say OS, right? And then I say EOF, right? So I type the EOF character. Let's say I say Control C, end file. So what I'm going to get as a result is a sorted list of this. So I'm going to get C Pune first, followed by hello, right? Assuming that alphabetically speaking. So CE Pune, hello, and then OS. Yeah. So that's the functionality of the sort program. Notice that in this case, it just reads from the standard input and writes to the standard output. If the standard and the way the standard input and standard output get initialized, they get initialized from the standard input and standard output of the shell. So wherever the shell was running, that's where the output gets printed, and wherever the shell was taking its standard input from, that's where it takes standard input from, right? Okay. So let's say if I wanted to sort a file, what I'll do is I'll say sort less than file.text. This less than descriptor is used for input redirection. Right? And I'm going to implement this using fork plus close 0, right? That's standard input, plus open file.text in read mode, right? And then exec sort, right? So I can use the same program to sort a file, right? I hope you all understand this by now, okay? All right, so I did, I sort, so I could also do something like this. I could say sort less than file.text greater than sorted file.text. That's a sorted.text. So this way I can, I'll sort the input file and print the output in a different file called sorted.txt, right? I could do this. Now let's take a more complicated example, right? Let's say I have a file called file.txt and I want to count the number of unique words in that file, right? So let's say I have a large file and I want to count the number of unique words in that file. So for example, if my file.txt looks like the following, let's say it is ABC. Let's use real words. So let's say hello, world, OS, hello, OS again, right? So let's say this was my file.txt. Then the answer I want is the number of unique words in this list, which is 3. Right? Hello, world, and OS. Hello is just repeating multiple times. So let's say I wanted to count the number of unique words in this file, right? And let's say the file is really large, and I want to do this in some way, right? So I'm going to use some UNIX utilities to try and do this. So first I'm going to sort the file. So I'm going to say sort less than file.txt and greater than some temporary file temp1. Need projector, right? So sort less than file.txt greater than temp1. So this is going to sort the file and put the sorted contents into temp1. So for example, if I sort this particular file here, what I'm going to get as sorted is hello, hello, OS, OS, world, right? That's the sorted list alphabetically, right? H comes before O and O comes before W, let's say. Okay? So I'm going to sort this list and I'm going to print the sorted list into this file called temp1. Then I'm going to, once this file is sorted, I'm going to invoke another utility called unique. So unique is a utility which takes a sorted input and tells you the and eliminates any duplicates, right? So it just retains the unique words, eliminates all the duplicates. So I'm going to say unique less than temp1, okay, greater than temp2. Okay. So in this example, when I run unique on this, what am I going to get? I'm going to get three words: hello, OS, world. Right? All duplicate entries are going to get removed. So only three words are going to remain in this file. All right. And once I've done that, then I'm going to invoke another utility called word count, WC. That's just going to count the number of words in this file. So I can say WC less than temp2. Right? And it's going to read its input from the standard input, all the other utilities, and it's going to write its standard output to the standard output. I haven't redirected the standard output here, so it's going to say 3 here on the standard output. That's the monitor in that particular example. Okay. So I'm going to say sort less than file.text greater than temp1, unique less than temp1 greater than temp2, wc less than temp2, and I get my answer. I wanted to count the number of unique words in the file. Right? This kind of thing works, but it's not very efficient, right? Let's say my file was very large. Let's say it was 1 terabyte in size. Then I need another file, temp1, which should be able to hold another 1 terabyte. So I need to read 1 terabyte of file.text and write 1 terabyte of sorted output. Then I need to read 1 terabyte of data and then write slightly smaller maybe data to temp2, and finally then the output is just one number, right? So it would have been better if I didn't use all this extra space. Also, I'll need to execute another command because all these temp1 and temp2 are just temporary things. This was not my original purpose, so I just basically just removed to free up space. I just said rm temp1 temp2, where rm basically just removes these files, right? This is one way to do it, but this is not a great way to do it, right? Ideally, it should have been something like this. I know that sort is a program that takes data from standard input and writes sorted data to standard output, right? In this case, we had attached file.text to its standard input, right? But on the standard output, we had attached temp1. Instead of attaching temp1, if I had some way of directly connecting the standard output of sort to the standard input of unique, right? Let's say this is unique standard input, and then unique standard output is connected directly to the standard input of word count wc, and then the standard output of this is connected to whatever the shell standard output was. Let's say it was a monitor. So that's it. If I had some way of connecting these programs in this way, things would have been much more efficient. I wouldn't have the need to actually create another file, and extra space is not needed, extra time to actually write that space is not needed, and I don't need to remove those files later on. If I could just connect the standard output of this program to the standard input of this program, then it'll be great. He's just writing to it and he's just reading from it. Okay. And this is possible on UNIX, all right? And the way it's done is these connections between the file descriptor, so standard output is nothing but file descriptor number 1, and standard input is nothing but file descriptor number 0, right? So these connections between the file descriptor of one program or one process to the file descriptor of another process is called a pipe, right? And you can create pipes using a system called UNIX, and we are going to see this next time, right? So we're going to create pipes between file descriptor number 0 of the sort program, or file descriptor number 1 of the sort program, and file descriptor number 0 of the unique program. Similarly, I'm going to create a pipe from file descriptor number 1 of the unique program to the file descriptor number 0 of the WC program. And with these two pipes, I'll have a much more efficient realization of my program, which was meant to count the number of unique words in a large file. Okay, I'm going to discuss the pipe system call next time. I will highly advise that you review all the material that we have done so far, and maybe even look at even go on Linux and say man pipe, or look at the course web page, and look at the next lecture notes to look at man pipe, look at the pipe semantics, so that when I discuss it next time, you are better prepared, right? So there's plenty of time between today and next Monday, which is our next lecture. So I would highly recommend that you try to get introduced to this pipe system call before we meet. Okay. All right. At this time, I'll take questions. SMIT? Please ask a question, SMIT. Cannot hear you. Okay. Let's take another question. Is there any other question today? Okay. So let's use these last 2 minutes to just, if there are no questions, any feedback? Am I going too fast? Am I going too slow? Yeah, VC. There's a question from VC.
Hello, good morning, sir. What is the relation between the FD table and PCB, process control block?
Okay, what is the relation between FD table and the process control block? We haven't talked about the process control block so far, so but they're two different things. Okay, and what are in general the process control block has a pointer to the FD table internally.
Thank you, sir.
Okay, another question from SMIT.
Sir, if we have a file descriptor 012 pointing to some other process that is running in the background, sir, and if we close that process, close the file descriptor, will it create a problem?
So the question is, if we have a file descriptor pointing to another process, and that process gets and I close the file descriptor, does it cause a problem? No. The flip question is, if I have a file descriptor pointing to another process and that process gets killed, then what happens? Then that file descriptor pointer becomes empty. So that file descriptor, the next time you call read or write on it, they will not succeed. Right? We're going to see this later. So you're going to see what are the semantics of a pipe. What happens if one end of the pipe dies? Then what happens to the other end? All this we're going to see. Okay, somebody wants to say, am I going too fast, too slow? Yeah, I mean, frankly. Okay. If there are nobody wants to say anything, I'll assume that I'm going at the right speed. So I've been looking at a UNIX system call abstraction, and I want to go through it in some level of detail so that we understand exactly what kind of operation, functionality an operating system provides us. As soon as we are done with the UNIX system call abstraction, I'm going to start looking inside the OS and see things like virtual memory, how the address space is implemented and all that. So all the traditional operating system topics we're going to cover very soon. But it's important to also look at it from the outside. So we are actually looking at an OS from the outside. We are saying, let's look at an OS, let's look at, let's say, UNIX, and see what are the system calls it provides. And because most of the modern operating systems are actually based on Unix, and we are also looking at, Linux is pretty much based on Unix, and Windows is also based on Unix, but except there's these small differences like fork and exec is not there, but create process is there, right? But they both have, for example, the notion of file descriptor tables. They both have the notion of open, read, write, close. They both have the notion of dupe, and they both have the notion of pipes, right? So these are all common to these modern operating systems, and so these are important concepts. So there's a question from VCE.
Sir, actually, this FD table is separate for each process. Like child process has its own FD table, parent has its own FD table. Yes.
Right.
Okay.
FD table is per process. Okay, there's a question on the text mode. So I think there was a question that if I open the file in append mode, then why will it overwrite? See, opening a file in append mode only initializes the offset, right? So if you open the file in append mode, it basically means that the offset is initialized to the end of the file as it stands now. But from then on, it the offsets are separate, so they can overwrite each other. So append mode is only used for initializing the offset. The whether the file was opened in append mode or not has no consequence later after the open call. How can a child process be larger? Okay, this is done. What happens when the child process? Can you look at the top question, please? What happens when the child process is executed using okay, this is fine. Let's go down. What if we already have an empty FD? I didn't understand the question. So as we said, if you already have an empty FD, I mean, I don't understand. So what are you talking about? Okay, if main child process. If main parent process is terminated, then its child process points to which process? Okay, points to using what? In general, every process has a parent process, and if the parent is terminated, then Linux has this thing that a process, if the process becomes an orphan process, then it is made to point to the first process in the system, the init process, right? So if an orphan process goes to the init process, basically. If a child has lost its parent, if a process has lost its parent, then it's an orphan, and it's given to the init process. So init process basically becomes its parent. But no, it's not very important. Okay, there's a question from GIT.
Good afternoon, sir.
Good afternoon.
So what's the difference between pipe and socket?
Sorry?
What's the difference between pipe and socket?
Okay, what's the difference between pipe and socket? Okay, I haven't discussed socket so far, but sockets are typically used for communicating with the outside world, right? So for network connections, which is over the over protocols like TCP and IP, pipes are used within two processes to communicate with each other. Pipes are more efficient because they only worry about processes within the thing. Sockets are more general. They allow communication across machines, so they need more metadata, and so they are slightly less efficient than pipes.
Thank you, sir.
Okay, it's time. Thank you, and see you on Monday.